Hey, so this is Joe, and this is the second video of the 12th chapter of Stewart's calculus, in other words, the second video of multivariable differential calculus. And so we are going to be talking about a new, I guess it should be new, vector operation that we're going to be dealing a lot with in this course, and it's called the dot product. And so don't let this fool you. It's not straight multiplication. You're not just multiplying the components of two vectors. What the dot product does is the following. So we define our two vectors up here generally by their components, and so we say the dot product between A and B, and we represent the dot product by this big black dot there, and it doesn't just mean multiply, it's a special operation. What that is the product, or the sum of the products of each respective component of the two vectors. So we multiply the x components of both these vectors together, add them to the product of the y components, and add them to the product of the z components. So an important thing to note about the dot product is that the result of the dot product between two vectors is a scalar. It's not a vector. This doesn't have any direction. This is just a number. This will just end up being a number. And so the reason the dot product is useful is for the following identity that you can prove from this, but that I'm not going to. I believe your book does, and you're not going to be responsible for this proof. But what's important about the dot product for us is this identity we have. So the dot product between two vectors A and B is equal to the actual product, so the real product, or like the straight product between the magnitude of A and the magnitude of B, and then the cosine of the angle in between them. So this theta is the angle in between them. So say we're in two-dimensional space. We have our A vector, we've got our B vector right here. Theta is going to be this angle right there, the angle in between them. And theta, we're always going to, this is something else that's important, we're always going to consider theta the angle that's between 0 and pi. So we have to adjust our theta accordingly. And so this identity right here is important because it allows us to identify perpendicular vectors, or orthogonal vectors, simply based on the vectors themselves, just based on their components, because we can find the this dot product, this value right there, this way. And then we can find, and then knowing those components, we can also find their magnitudes, and from that we can find theta. We can find when that's 90 degrees. And even easier, because remember, when theta is 90 degrees, cosine is going to end up being 0. We get this corollary right here, the dot product between A and B. When that's 0, theta is going to be 90 degrees. So this is very important for later on in the course, because the dot product is very important for later on in the course because it allows us to identify the angle between two vectors, and more importantly, it allows us to know when they're perpendicular to one another. But also what you're going to need to do in this course sometimes is basically just do vector algebra, and so just be able to do algebra with these new operations that we're going to be learning between vectors. And so in the next slide I'm going to show you some properties of the dot product, some algebraic properties of the dot product. So the three significant properties to remember about the dot product are these ones. So the first one, the dot product between two vectors A and B is equal to the dot product between the same two vectors but B and A. This is basically, this property shows us that it doesn't matter which order we write out a dot product in. We can write it out in whatever order we want, this dot product, and it'll end up having the same result. This is not true for the next operation we're going to learn in the next video, the cross product. But so remember that this is true for the dot product. The second property is kind of a distributive property of sorts. If we have the dot product between A and then the sum of two vectors, we can distribute that A and the dot product inside. So we'd get the dot product between A and B plus the dot product between A and C if we have the dot product between A and the sum of these two vectors. So this is kind of a distributive property. And then we have a sort of like scalar multiplication of a dot product. And so all you have to remember for this is you just do scalar multiplication with one of the vectors inside the parentheses. So you can multiply that c by either the vector a or the vector b, but don't do it by both, because the c will end up showing up in the result of this dot product, because remember, you multiply both the components of these two vectors together and then add them. So there's going to be a c, so it'll end up looking something like a c a1 b1 plus a c a2 b2 plus a c a3 b3. And if you were to multiply the c by both of the vectors, you'd end up having c squareds, which wouldn't really make too much sense. So yeah, just multiply that c by one of the two vectors. So those are the two dot product properties. And now we're going to be talking about vector projections, which is the kind of last really important reason that we're going to be using the dot product later on in this course. Okay, so vector projections work like this. Say we have two vectors. We have a vector A and we have a vector B. If we want to find the vector projection of B on A, what we're really trying to do is find how much of B moves in the direction of A. So instead of finding a component of B with respect to either the x, the y, or the z axis, we're trying to find a component of B with respect to A. So it's kind of a relative thing. And so in order to do that, we don't have to, but and so what that projection would look like is this vector right here. It's moving in the vector's in the direction of A, but it's acting kind of as a component of B, and we write that vector out as the projection sub A of B. So it's the projection of B onto A. And so there are two things that we can do with this. So first, you need to note that this comp AB, what that is that's called a scalar projection, and what it is it's the magnitude of the vector, the projection of vector B on A. So that's a magnitude right there. And looking at this algebraically, it looks like all we need to do to find that magnitude is take the magnitude of B and multiply it by the cosine of theta. And that's true. So the magnitude of the projected vector of B on A is really just the magnitude of B times cosine theta. That's some basic trigonometry right there. But we can use this, but if you remember, if you have two vectors, the dot product between B and A is equal to the magnitude of A times the magnitude of B times the cosine in between. All we're missing in this expression is the magnitude of A. So that means that the dot product, so if we start off with the dot product of A and B is equal to the magnitude of A times the magnitude of B times cosine theta. If we divide over the magnitude of A, so we have this right here, this expression is equal to the magnitude of B times cosine theta, which we know is equal to the scalar projection of B on A, and that's what this is called. This is called the scalar projection. So this is another reason why the dot product is really helpful, is it allows us to find the magnitude of this projected vector. But not only that, it also helps us find the that projected vector itself as a vector. And all we need to do to find that is we need to give it direction. And in order to give it direction, give it the direction of A, we multiply the scalar projection by the unit vector of A. So we have this is equal to the unit vector of A times the scalar projection of B on A, which will end up being A over its magnitude times the dot product between A and B over the magnitude of A. And so we can combine those two magnitudes, and we will get the vector A times the dot product between A and B and the magnitude of A squared. And that is how we express the projection of B on vector B on vector A. And so this will end up being a vector because, right, this is just some scalar multiplication. This whole thing right here, that's just going to be a number. That's a scalar, and we're multiplying it by a vector. So in doing that, we're preserving the direction of A, because all the components of A will have the same proportions to one another. It's just the magnitude of A that's changing, and the way that the magnitude of A is changing is this magnitude will turn into the magnitude of the scalar projection of B on A. So that's how projections work, and this is going to be very important later on when we do things like take directional derivatives. That might sound very confusing, and it is a little bit confusing, but they're very cool. So now let's do a couple practice problems using the dot product, some problems that you might encounter in your course. So we'll do number 11 on page 830 in your book, and what the problem asks from us is, given this diagram right here where we have three vectors u, v, and w, they all have the same magnitude, and the magnitude of u is 1, so they're all unit vectors. Given this setup, find the dot product between u and v, and find the dot product between u and w. So the first thing that we need to notice here is this kind of forms an equilateral triangle. So all these angles here are going to be 60 degrees. 60 degrees, 60 degrees. And so this makes finding the dot product between u and v relatively easy, because both of their tails are together, so that means that the angle between them is 60. And so given our property that the magnitude of the dot product between u and v will equal the magnitude of u times the magnitude of v times the cosine of the angle in between them, since both of these magnitudes are going to be 1, we've got 1 times the cosine of 60 degrees, and the cosine of 60 degrees is going to be a half. So that dot product is pretty easy, that's a half. And so right here we might be tempted to say, when we're finding the dot product between u and w, oh, we'll just do the same thing, the angle between them is 60 degrees. Well, not quite, because the angle between the tip of u and the tail of w is 60 degrees. But that's not the angle between them. What we need to do to find the angle between them is transpose u so that both of the tails of u and v are touching. And we're allowed to do that. We just need to maintain its direction and its the direction and the magnitude of u, so that it's the same vector. And so if we can bring u down like this, and then the angle between them is going to be, using our geometry skills, it's going to be 120, right? Because this is going to be a straight line. That angle would be the total angle is 180, 120 plus 60 is 180. So the angle between u and w is 120 degrees. And given the stipulation of this identity here, this dot product identity, the theta, the angle in between them, needs to be between 0 and pi, so between 0 and 180. So since this is 120, it looks like we're good. So we can apply our identity, the magnitude of u times the magnitude of v times the cosine of the angle between them. We'll get a 1, because the magnitude of u and w is both 1, times the cosine of 120, and the cosine of 120 is negative a half. So that's that dot product. So that's not too bad. That just takes some kind of rearranging of vectors in space. So now let's go on and do a little bit more a projection problem, which is the other big kind of problem that you're going to need to be dealing with. Alright, so we're doing number 43 on page 831 in your book. And what this question asks us is to find both the vector projection of B on A and the scalar projection of B on A. And since those two are related, it's not going to be too much work to find the both of them. And we're going to find this given that A is 2i minus j plus 4k, and b is j plus a half k. And so b is the vector that we're trying to project onto A. And so let's rewrite these vectors in terms of our bracket notation. So we're just going to get the coefficients of each of these the standard basis vectors. So we got a 2i, so we'll get a 2, negative 1j, that's a negative 1, and 4. Okay, so this is A, and B, since there's no I written out, we have an implied 0 for the x component, and then we've got a 1 for the y component, for the j component, and we've got a 1/2 for the z component, because it's the coefficient of k. So now we can start applying our formula. So we've got the scalar projection of B on A, is going to be the dot product between A and B over the magnitude of A. So let's find the dot product between A and B. So we multiply all of the corresponding components and then add them up. So we'll get 2 times 0 is 0, plus -1 times 1, so plus a -1, that'll be -1, plus 4 times a half, so that's going to be plus a 2, and then over, and we use our magnitude formula here, so we're going to get the square root of 2 squared, the x component squared, which is going to be 4, plus 1, the y component squared, which is 1 squared, which is going to be a 1, and then plus the z component squared, which is going to be a 16. And so we will get 1 over root 21. And so that's the scalar projection of A on B. And now we need to find the vector projection of, sorry, that was the scalar projection of B on A. Now we need to find the vector projection, scalar projection of B on A. And all we do is we multiply the unit vector of A by our scalar projection of B on A. So we have our 1 over root 21, and we've got our unit vector is A over the magnitude of A. So we're going to get 1 over root 21 times A is 2, -1, 4, and its magnitude, as we found here, which is this magnitude, is root 21. So that is 1 over root 21 times 2, -1, and 4. And if you want to write this as just everything inside the brackets, just distribute that 1 over root 21 to all the components. But otherwise, that is the projection of the vector of B projected on A. So there you go. That is pretty much it for dot products. Stay tuned for the rest of this chapter and hopefully the rest of this course. Thanks for watching.